We'll now discuss the composition of functions. This means taking functions and composing them into new functions, turning them into new functions. So here's a definition. Suppose we have functions f from a to b and g from b to c. So we have two functions. F is a function from set A to set B, and g is a function from set B into set C. So notice that the codomain of f is the same as the domain of g. So suppose we have two functions like this, then we can define their composition. The composition of f and g, which is denoted like this, g circle f. So notice it's the composition of f and g, and it's denoted g circle f. So the order is the opposite of what you might think. So this is a new function, g circle f, that's the name of the function. This is the whole name, g circle f. We can give it a new name if we want to, but this is the basic name, g circle f. And it's a function from A to C. So it sort of bypasses B. It goes directly from A to C. And it's defined as follows. It's defined by g of f of x for all x in A. Let's look at an example. So suppose we have the following functions f and g, right? So f is a function from A to B. G is a function from B to C. Let's take a look. So for this function, for f, for example, it takes 0 and it gives an output of 2. It takes 1 and it gives an output of 3. It takes 2 and gives an output of 2, and so on. And then function g takes 1, gives an output of 7, takes 2, gives an output of 4, and so on. So those are functions f and g. So what we have is a situation where f is a function from A to B and g is a function from B to C. So we can define g circle f, or g of f, and it's the new function that goes directly, for example, from 0 to 4. So why is that? Well, if you follow f, you start at 0 and go to 2, and then follow g, go from 2 to 4. So g circle f says, well, bypass that whole middle thing. Just go directly from 0 to 4. The idea is that g circle f is g after f. One way to read this, it's not the technical way to read it, but the intuitive way to read this is g after f. G after f, meaning first do f and then apply g to that result. So for example, if you have this 1 here, first apply f, so that gives you 3. Then apply g, so that goes from 3 to 5. So the result, so what we have is, for an input of 1, our final output is 5. So for g circle f, the input would be 1 and the output is 5. So again, g circle f means g after f. First apply f, then apply g. Let's look at another example. Let's say we have a set A equals little a, b, c. Set B contains 0 and 1, and set C contains 1, 2, and 3. Let's say we have a function f from A to B defined like this. It's a set of ordered pairs, so A comma 0, B comma 1, C comma 0. And then let's say we have a function g from B to C defined like this. Whoops, missing a curly brace there. All right, and let g be a function from B to C containing these ordered pairs. All right, so we have a function from A to B and another function from B to C, so we can define composition. So what is g circle f? So we want to write it as a set of ordered pairs. Okay, well, it's going to be a new function from A to C, and it's going to be defined as follows. G circle f. So it's a set of ordered pairs. It's a function from A to C. So we have to deal with all the inputs from A. All the elements of A are inputs to the function. So we have an ordered pair starting with A, we have an ordered pair starting with B, and an ordered pair starting with C. Now, what's the second part of each pair? So for the first order pair, we start with A, And then the second part of the pair is the output of the function. What's the output of the function? Well, it's going to be g of f of a. In other words, 3. So we have an ordered pair a comma 3. For the next ordered pair, we start with b, that's the input, and the output is going to be g of f of b. So what is that? Well, f of b is, well, what is f of b? It's 1. Well, what is g of 1? Well, g of 1 is 1. So we end up with this pair b comma 1. Next, we have a pair c comma g of f of c. Well, what is g of f of c? Well, what is f of c? So f of c is 0. What is g of 0? G of 0 is 3. So we end up with the pair c comma 3. Now, what about f circle g? So this was g circle f. What about f circle g? So here's the thing. F circle g doesn't actually exist. Why? Since the codomain of g, which is c, right? The codomain of g is not equal to the domain of f, which is a. So remember, in order for us to have g circle f worked because f goes from a to b and g goes from b to c. But f circle g doesn't exist. In order for it to exist, we need to have that the codomain of g is equal to the domain of f. Think about it. What does f circle g mean? It means f after g. In other words, first do g and then do f applied to those results. Well, that means that the results of g, meaning the codomain of g, has to be equal to the domain of f, right? Because the idea is that you do g, you get some outputs, and then you apply f to those outputs. So the codomain of g needs to be equal to the domain of f. But that's not the case here, right? The codomain of g is the set c. The domain of f is the set a. C and a are not equal to each other. So therefore, f circle g doesn't exist. Let's look at another example, and let's try to answer the question, is function composition commutative? So consider the functions f and g from the set of real numbers to the set of real numbers. Okay, so what we're saying here is we're going to be talking about two functions, and they're called f and g, and they are both from the set R to the set R. So this is just a shorthand. Instead of writing f is a function from R to R and g is a function from R to R, we just can write it like this. F and g are both functions from R to R. So consider these functions defined by the rules as follows. F of x is x squared plus x, and g of x is x plus 1. All right, so those are our functions. Let's try to find what is g of f. All right, g circle f. So g circle f is a new function from R to R, right? In other words, here f and g both have the same domain and codomain as each other, so we can easily define g circle f as a function from R to R. And let's figure out what the rule for that function is, what the formula for that function is. So it's going to be g of f of x, right? That's just based on the definition of function composition. So g of f of x. Well, what is that? So that means we first have to expand f of x, and then we'll apply g to that. So that means g of f of x. Well, f of x is x squared plus x. So we have g of x squared plus x. And what is x squared plus x given to g? So g says, take whatever you give me and add 1 to it. So if you give g x squared plus x, it'll take x squared plus x and add 1 to it. So we're left with x squared plus x plus 1. That's the formula for g circle f. How about f circle g? So f circle g is another function from the set of real numbers to the set of real numbers. So f circle g means f of g. You first do g, and then you apply f to that. So it's defined as follows. It's going to be f of g of x. Now, what is g of x? G of x is x plus 1. So this is f of x plus 1. Now, what does f of x say? So f of x says, take the input and do it, square it, and then add the input to that. So we are going to take x plus 1 and square it, and then add x plus 1. So we're going to be x plus 1 squared plus x plus 1. That if we expand the x plus 1 squared, we have x squared plus 2x plus 1, and then plus x plus 1. And if we simplify that, that comes out to be x squared plus 3x plus 2. Notice that G circle F is x squared plus x plus 1. F circle G is x squared plus 3x plus 2. So notice that G circle F is not equal to F circle G, right? This formula produces different results in many cases than this formula. So these two functions are not equal to each other. So here's a remark. Function composition is not commutative. How do we know that? Well, we see that from this example that we just did. In other words, the order matters. G circle F is not necessarily the same as F circle G. Function composition is not commutative. That is, given any functions G and F, it is not necessarily the case that F circle G equals G circle F, even if they both exist, right? So there are some cases where only one of them exists and the other one doesn't exist. But even if they both exist, they're not necessarily going to be equal. As we saw in this previous example, they both existed and yet they weren't equal to each other. Now let me ask you, is it always the case that F circle G is not equal to G circle F? Right here I'm saying it is not necessarily the case that F circle G equals G circle F. And we see an example where they're not equal. But does that mean that they're never going to be equal? Well, no, it doesn't mean that. It just means that they don't have to be equal, but they presumably could be equal. And now I'll show you an example where F circle G is in fact equal to G circle F. So here's an example. Consider two more functions, f and g, from R to R, defined by f of x equals x plus 1 and g of x equals x minus 1. Okay, now these are two different functions. One does x plus 1, one does x minus 1. Now let's find the compositions. So f circle g is a new function from R to R, defined by, well, that's f of g of x. So g of x is x minus 1. So that's f of x minus 1. Now, f of x says take the input and add 1 to it. So we have x minus 1 plus 1, and that comes out to be x. So f of g of x is just equal to x. Next, what is g circle f? So g circle f is also a function from the real numbers to the real numbers, and it is defined as follows. It's g of f of x. So that's g of x plus 1, which is x plus 1 minus 1, which is x. So notice here in this example, f circle g is equal to g circle f. So just because we are saying that it is not necessarily the case that they're equal, doesn't mean that they can't be equal, right? Obviously, they could be equal, but there is no rule that says that they have to be equal. So that's what it means to say that function composition is not commutative, meaning it doesn't have to be commutative. There are some cases where it might be, but as a general rule, it would not be correct to say that it is always that they're always going to be equal. All right, now let's ask, is function composition associative? So different property, and we'll see exactly what that means. So here I'm just stating it as a fact. I'm not going to prove it. The proof is the proof is not long. It's in the book. It's just tedious, and I don't want to show it. But here's the fact: function composition is associative. What does that mean? What does associative mean? So that is, if we have functions f from a to b, and g from b to c, and h from c to d, it is always the case that h circle g and then circle f is going to be equal to h circle g circle f. That's what associativity means, that this is equal to this. Notice in other words, what does associativity mean? It means that the way we group things together doesn't matter. That's what associative means. When I say an operation is associative, it means that the way you group things together with parentheses is insignificant. And in this case, the reason that they're equal, the reason that composition is associative is that both this on the left and this on the right both end up being equal to h of g of f of x. So the way we group things together with parentheses doesn't change anything. It always comes out to be h of g of f of x. Okay, so we just stated as a fact that function composition is associative. Let's just do an example where we have three functions and we compose the three functions together. So let's say we have functions f, g, and h, and they're all functions from the real numbers to the real numbers. And let's say they're defined as follows. F of x is x squared plus x, like before. G of x is x plus 1, like before. And h of x is just 2x, 2 times x. Now, what is f, circle g, circle h? Now, you might say, well, don't we have to put parentheses? In other words, are we going to be grouping f with g, or are we going to be grouping g with h? Well, the thing is, because function composition is associative, as we saw here, we don't need parentheses, because parentheses wouldn't change anything, because either way, it would come out to be h of g of f of x, or in this case, actually, f of g of h of x, right? But the point is, the adding parentheses wouldn't change anything, so parentheses are not required. We saw a similar idea, if you remember, all the way back in set operations, in very beginning of the semester. We saw that certain operations with sets are associative, and we said that with those operations, since they're associative, we don't need to use parentheses, because the way we group things together doesn't matter if the operation is associative. So here's another example where we have an associative operation, so we don't need to have parentheses. All right, so this is equal to f of g of h of x. Well, let's figure that out. So we have to work from the inside out. H of x is 2x, so we're going to have f of g of 2x. Now, what is g of 2x? So g says take the input and add 1 to it. So if the input is 2x, then we're going to get from g 2x plus 1. So what we have now is f of 2x plus 1. Well, what does f say to do? Well, f says take the input, square it, and add the input to that. So we're going to take 2x plus 1 and square it, and then add 2x plus 1. So we have 2x plus 1 squared plus 2x plus 1. If we expand that, we get 4x squared plus 4x plus 1, then of course plus 2x plus 1. And if we simplify, we get 4x squared plus 6x plus 2.